I'm Pradeep Shenoy, and I am the compute power technologist at TI. And I work in TI's systems engineering and marketing organization. I've been working on educational resources for TI for a number of years, but pretty much ever since I started. Everything from the most basic data sheet or an application note that goes along with it, along with some of the more premier educational resources that we have, like the Power Supply Design Seminar.
I'm Art Kay, and I'm an applications engineer. But what I really like doing is I give seminars, live seminars. I'll travel around the world and meet different customers, and that's quite fun. But also create the online videos of Precision Labs.
My name is Stephen Dunbar. I'm a field application engineer here at Texas Instruments. I have one of the more really interesting jobs at TI where I get to help customers use TI products. I use the educational resources as part of my job on a daily basis. So I have my favorite tools, the Pocket Reference Guide, the Power Stage Designer, for instance. So I screenshot that all the time when I'm collaborating with my customers on their work.
I think the main purpose, or at least one of the main purposes of these tools, is just to help our customers solve their day-to-day problems. How can they optimize their circuit? How can they design their circuit? How do I make sure that this is going to function properly?
So one of the things that I find really interesting about our educational resources is they help bridge that gap from the ideal that you might learn in a university setting to practical, like how you actually implement something.
So when I first got out of college, one of the first things I did was characterize the resistors in an IC. And I thought, well, this is rather strange. A resistor is a resistor, but what I had to do is measure the temperature coefficient of the resistor. And I learned a lot about, how resistors change over temperature. And it was really eye-opening to learn how complex things are beyond the idealized version of what you get in college.
As we hook these things up, the non-ideal nature of actual physical devices comes into play, and that's why there's so many parts out there to address the various needs.
I remember when I was first starting out as a graduate from college, I didn't know how to do some real basic things, but I saw that over time as I became a manager of a team or manager of bigger teams, I needed to help train and teach and equip the new people that were coming along on my teams. And so I had like a different perspective of like, hey, what resources are out there that I can give to the people on my team to help them, solve whatever problems they're trying to solve or bridge whatever knowledge gaps they might have.
I think it really fills in a lot of gaps, like a lot of engineers, especially if they're making a transition in their career, maybe.
Right. That's a good point.
Maybe they're an analog engineer and they need to do a power supply, or they've been doing software engineering and they need to do op amps. Right. It's a great way to figure out what you don't know.
Yeah.
Right?
No,
so you go read some of these materials like, oh, I maybe remember that, or I had no idea I had to worry about that.
I've even had some customers who are professors, some who are physicists, let's say, or their expertise is, let's say, developing a bridge sensor, but then they have to connect it to the electronics, and they need to understand, like, how does the electronics work, and that's secondary to them. It's not their primary field of knowledge.
Yeah, that's a really good point, where you have these people that are very smart. They know a lot about something else, and they need to pivot to some other thing to get whatever their main thing done.
In college, when you learn an op amp, you learn it has basically a voltage-controlled voltage source. Maybe you learn a little bit about bandwidth, but you don't learn about things like input and output swing, stability, noise, input offset voltage and bias current, and all these other error sources. And those are all covered in Precision Labs. So I had a hand in developing it and creating it. And what I really like about it is that it's a sequenced course curriculum, really. It starts with basic topics and then moves on to more and more complicated topics. It's great for anybody who's all the way from a new college grad up to a senior engineer. There's an op-amp Precision Labs, there's data converter Precision Labs, and all sorts of other product types are covered by this. There's thousands of hours of content out there.
Yeah, I've used your videos actually myself. I use them to freshen up my own skills, especially on the noise and stability. Uh, it's been very helpful to me, and they're very well done. They're short, 8-10 minute videos, and you can watch them over and over again and pick up the material that way.
One of the tools that I like to use is Power Stage Designer. And what I like about that is it's generic. It has a lot of different topologies for power conversion. And you can very easily, quickly look at different operating conditions, different input voltages, different output current levels, and you can look at what are the somewhat idealized, but the waveforms of the converter. What does the inductor in the current in the inductor look like? What is the voltage in the capacitor, or the current through the switches, or whatever you might be interested in looking at? And it really helps to design the converter, and it'll help calculate, RMS currents and peak currents and things like that. You don't have to do like a really big, super detailed circuit simulation always. Some of these tools that we have are trying to make it simple.
I'm personally working on a voltmeter design problem right now, and that requires a lot of very tight drift performance, like over temperature. Like what sort of an op amp do you need to implement a very low drift system? It's a special part, and those types of topics are what you learn about in like the op amp seminars.
In the power supply design seminar, what you will usually see is both a white paper and a presentation, sometimes even a video. And what the topic usually starts off with is some sort of background information on what's the application that we're trying to target. Maybe we're trying to design a dual active bridge converter, and where would you design a dual active bridge converter? And how does it work? What are the operating waveforms? What are the switching timing? And then you might talk about the control that's used to actually design the closed loop control for this dual active bridge converter. Or maybe you would have some part of the presentation or the white paper discuss how do you select some of the components around this converter. So maybe how do you design the transformer, or how do you do the gate drivers or the bias supplies for this converter, or things like that. There's also some of the seminars that are more focused on how do you lay out a circuit board for a power supply. What are some of the guidelines and tips and tricks that you didn't give you examples of, okay, here's a good layout, here's a bad layout. Art, you mentioned it before, just, you learn a bunch of idealized things in school, but making it practical, making that jump to how do I apply this to the actual piece of equipment that I'm trying to build and test and ensure that it's going to work properly over all the different conditions that I need to get it to work. That's where these sorts of very specialized tools, I think, really help.
It's not just videos or pictures or papers. There's entire startup guides that are designed to, again, accelerate the user experience through what can be a pretty hard learning curve. I mean, some of these topics, even with all the tools that are available, it's going to take some time to go through the topic, just because it's the nature of that type of material. If you want to learn embedded processing, there's an entire series there of content that goes from absolute starting point, how do you get started with an ARM M0 class processor, through the development tools all the way up to a Linux class type of device. So it's very deep, very well done, and very current.
I've used the Analog Design Journal for a lot of that kind of stuff, where it's on a specific topic, usually with a specific context. Like, you're in this application and you're trying to do something like, how do I generate a negative voltage rail from a positive voltage rail? And then it goes through, okay, here's how you make an inverting buck boost converter, and here's how you can use a regular buck converter to do that. And it explains some of the challenges that you might have to face. And I remember being able to address an immediate challenge that I was meeting with one of our Analog Design Journal articles.
Those are very interesting because they are outlining a specific, often industry trend, like a certain part was developed to solve a certain particular problem. Maybe it was USB Type-C and some new controller for that, for instance. So yes, there's a part in there, but the reason the part exists is because there's a standard now that needs to be supported. A lot of people go to those design journals to learn basically new technology and where is the world of technology going.
Engineers are curious by nature, right? And that's where these educational resources really come in, is to help meet that voracious desire for people to learn in, structured way at times, or sometimes ad hoc, whatever it's needed. But these engineers really want to know how to solve their problems, how to understand their problems to begin with.
So having these foundational sorts of materials is super critical just to getting everybody through their design cycle as quickly as possible.
I was, born to be a teacher. I enjoy, let's say, taking complex concepts and simplifying them.
It's really getting back to always being a master of the basics, mastering the fundamentals.
Whether it's fundamental topics or more advanced, these engineering resources and various tools to support engineers really are designed to help accelerate them, help them to understand what they're trying to solve, and help them to quickly get to their desired solution.